Okay, thank you all for coming today. I know many of your classmates decided against it, but the show must go on even though there's an exam this week. I do have a few announcements to start with that various organizations have asked me to make, and these will be in the notes so you can check it out. AEA, one of the pre-med associations, has a meeting on Wednesday of this week, 6 to 8 p.m., just two doors down from here, so right after class. So that's one that you can check out. And then I've been asked by the Student Programming Board to advertise a comedy show which conflicts with that, so you have to decide between pre-medical stuff and comedy, I guess. Jenny Segrino, who I don't think I've ever heard of, but I'm old, so that doesn't mean she's not good. She's performing Wednesday also in the Student Center Theater, and so if you need something to decompress after the exam this week, that might be a good option. And then there's one other thing that I forgot to put in here. I meant to, but I forgot. The Student Nutrition Association has a meeting tonight. So this is for people, you don't have to be a nutrition major. It's just anyone that's interested in the field of nutrition as a profession or as a hobby. And they have a meeting in the Cameron building. I think they run that little cafe over there, which I've never been to, but they have a student-run cafe over in Cameron. And that's tonight, I believe it's right after class at 5:30, so you'd have to hustle over there. Okay, so those are some of the announcements that I was asked to make. There'll be more later in the week, but we have to get going because there are many things to get to this week. We would ideally want to finish Chapter 4 this week because that's what the homework is about, and we started it last week with the VSCPR. So the first topic in Chapter 4 was determining the shapes of molecules, and that's a lot of what we talked about last Wednesday. And so here's a summary of that. We went through all of these individually in class, and now here's a little table. And remember that the shape of a molecule is determined by the AXE notation, where X is the number of atoms bonded to the central atom, E is the number of lone pairs, and depending on what combination of those you have, you're going to get different shapes for the molecule. So this first column here, AX2, AX3 through AX6, are what we call the electron group arrangements. Those are the 5 basic shapes, which also then double as the geometry if there are no lone pairs. And then when you add lone pairs, the geometry changes, and you give it a different name to show the shape of the atoms themselves, ignoring lone pairs. So that's what I went through last time, and the things we're going to talk about today are going to follow directly from that. So one of the things that the VSCPR geometry allows you to do is it allows you to predict the polarity of the entire molecule. So in Chapter 3, which is a topic that will come up on the test, we talked about the polarity of bonds and how they range from nonpolar, if it's 2 atoms with the same electronegativity, all the way to ionic, and then there's all these different, all this continuum in between where the polarity of the bond is determined by the electronegativity difference. So if we're going to talk about the polarity of a molecule now, which is a collection of more than 2 atoms, this is going to play a part in that, but also the geometry is important as well. So first let's review polarity quickly. So remember that the polarity is defined as having a direction towards the more electronegative atom. Now, as we said, the more electronegative atom in the bond is going to be the one that has the partial negative charge. And there's also this vector notation for it. So we had hydrogen bonded to fluorine. Fluorine is more electronegative, so it carries the partial minus charge. And there's a partial positive on hydrogen. So that means there's a net imbalance of electron density, but it doesn't mean that an electron is completely transferred between the two, as you would have in an ionic bond. And then the other way to indicate this is with a vector that points towards the more electronegative atom. So that's kind of the convention we use for defining the direction of polarity in a polar bond. And so if you're going to have a polar bond, you need to have 2 atoms that have different electronegativities, and then the direction is given as I just determined. And then we also talked about the magnitude of polarity. Now, we didn't quantify this numerically, but we talked about how to rank bonds in terms of most polar to least polar or vice versa, and that depends on the difference in electronegativity. So if the 2 atoms have different electronegativity values, and then you take the absolute value of that difference, it tells you how polar the bond is. So, for example, if we have carbon bonded to all of the halogens, and we want to rank them from most polar to least polar, same atom carbon bonded to all of them. Carbon is less electronegative than just about all of the halogens. So the biggest difference in electronegativity is going to be for carbon and fluorine. So you have your delta plus, delta minus, but that's going to be the largest polarity. This is going to be a little bit less polar because the difference between carbon and chlorine is not quite as big. This will be less polar. And then carbon and iodine, a good thing to remember for the test too, is that carbon and iodine have basically the same electronegativity, so this is nonpolar. Alright, so that's how we rank polar bonds. It's determined by the difference in electronegativity between the two atoms that are bonded to each other. And for the carbon-halogen series, it goes in this order, where fluorine is more electronegative and iodine is the least electronegative, and those give you the different polar bonds. Okay, so that's what we had for polar bonds. And then what we're going to define today is what's called molecular polarity. So that's the polarity of an entire molecule. So using the concepts we just discussed for polar bonds, you could easily determine and rank the polarity of diatomic molecules that only have two atoms in it. It just goes as we talked about. But if you want to talk about the polarity of a molecule that's a little bit more complicated, like we've started discussing last time at the beginning of chapter 4, we need to define polarity for the entire molecule. So what's the definition of molecular polarity? Just like it is for individual bond polarity, it's an uneven distribution of charge. But it's over a whole molecule or a large portion of it. Alright, now we're not going to talk about the quantitative aspects of molecular polarity either, but it can be measured and quantified, and the unit for this is what's called the debye, abbreviated with a capital D, and it's a very small quantity because we're talking about individual molecules which have very little charge associated with them on an absolute scale. And so it's 3.34 times 10 to the minus 30 coulombs times meter. So a polarity is basically a charge over a distance is what it boils down to. C here is the unit coulombs, which is the standard SI unit for charge. So like I said, this is not something we're going to see directly, but it's a little bit of contextual background. And then this quantifies what's called the dipole moment, which is another way of saying the magnitude of the polarity, and it's abbreviated with the Greek letter mu. Alright, so this is just to sort of prepare you for maybe some later courses you'll take in physical chemistry where you're going to be a little bit more quantitative about this. In this course, we're just going to talk about qualitative molecular polarity, which is basically, is the molecule polar or not, and in some cases maybe ranking the polarity of similar molecules using some of the concepts we'll talk about. We're not going to talk about the quantitative aspects of molecular polarity. So there's two things that we need to predict the molecular polarity. The first thing is that the molecule must have polar bonds. So if you have a molecule that has entirely nonpolar bonds, there cannot be any uneven distribution of charge, because in polar bonds the electrons are shared exactly in nonpolar bonds electrons are shared equally. So your molecule must have polar bonds if it's going to have net polarity. And so that means certain types of molecules, which we call homoatomic, these are molecules that have only one type of atom or one type of element in them. So the simple diatomics like N2 or other elements form larger molecules like P4, S8. These ones cannot be polar because all of the individual bonds in these molecules are going to be nonpolar, and so there can't be a net distribution of charge over the molecule. So if it's the same atom bonded to itself, it cannot be polar. So when you're doing problems that ask you to select polar or nonpolar molecules, or most polar or least polar, if you see something that has only one type of element in it, and especially if it's a simple diatomic like N2, O2, Cl2, whatever, which is very common, those ones can't be polar, so you can automatically know that without even thinking about anything else. However, for other more complicated molecules, you need to think about also the shape of the molecule, and that's where the VSCPR comes into play. So what I'll say right here before getting into all the nitty-gritty of it is that just because a molecule has polar bonds does not mean that it's polar in net. So the presence of polar bonds does not guarantee that a molecule will be polar. So if any of you are aspiring lawyers, which I'm not sure there's many in a chemistry class, but if any of you are, the language they like to use in law is, so polar bonds is a necessary but not sufficient condition to make a polar molecule. So necessary but insufficient. So you have to have polar bonds, but just because it has polar bonds does not mean that it will be polar, is what I'm trying to say here. So what then determines it is going to be the geometry of the molecule. And so let's look at some examples then to understand how different geometries can play into the overall molecular polarity. So I'm going to give you a few examples here where we have molecules with polar bonds, but it ends up being in net a nonpolar molecule. And so the way this works is that each of the bonds has a dipole associated with it. You have that vector that points towards the more electronegative atom. But in some situations, the individual dipoles of the bonds cancel out. So even though the bonds are polar, those polarities that are associated with each bond cancel each other out. And that results in a molecule that's nonpolar. All right. So I think the easiest one to see would be any linear triatomic molecule. So, for example, let's do CO2. So if we have CO2, this is an AX2 linear molecule. We can draw lone pairs on oxygen, but they don't really matter for polarity, but they're there. So that would be the Lewis structure for CO2, and it is a linear molecule, so I'm showing that geometry indicated fairly accurately here. And so if we think about the bond dipoles in this molecule, oxygen is significantly more electronegative than carbon, so there's going to be, each bond is going to be polarized towards oxygen. But you have that one that points from right to left as I've drawn it. You have an equal and opposite dipole from left to right, and so the two end up canceling each other out. So you'd have a delta minus, and then really two delta plus because there's two polar bonds. But in net, this molecule is unpolar because the two bond dipoles cancel each other out. One's pointing to the right, and there's an exactly identical one pointing to the left that cancels it out. So you want to almost think about this like vectors. So if you've taken physics class especially, that might be a good way for you to think about it, where you have two vectors that are pulling in opposite directions, and in net they have no pole on the molecule. So one way to think about it, it's not really what's happening, but think about if you had, so oxygen on one side is pulling electrons towards itself, oxygen on the other side is pulling the electrons towards itself at the same magnitude, and so those net poles cancel each other out. You wouldn't have any imbalance of charge there. So CO2 is an example of a nonpolar molecule. Now there are other geometries that are maybe less intuitive than this, but the same thing happens. So if you have BF3, which is trigonoplanar, there's a bunch of lone pairs on fluorine that I won't draw in, but they're all there. You're going to have bond dipoles pointing towards each fluorine. All right, and like this one's not as easy to visualize because you don't just have two that are tugging in opposite directions. You have three all oriented in different directions in space. But if you were to separate these vectors into x and y components, the x and y components would individually cancel each other out, and this would also be nonpolar. All right, or imagine that you have three fluorines all pulling on boron with equal strength. That boron is not going to move in any one direction. It's going to be stuck right there. That's kind of a pictorial way to think about it. So this would be also nonpolar, and then it works in three dimensions as well. If we have carbon tetrafluoride, which is tetrahedral, certainly not intuitive, but these all cancel each other out as well. So you have bond dipoles pointing towards each fluorine that in net cancel each other out, so you have no net polarity. So all these are examples of nonpolar molecules. We're going to systematize this a little bit later, but these are all situations where the bonds themselves are quite polar. Oxygen and fluorine are both very electronegative, and they're significantly more electronegative than what they're bonded to. So there are individual polar bonds, but those polar bonds cancel each other out, and so the molecule itself is still considered nonpolar. Now let's look at examples where you have polar bonds, but the molecule itself is polar. So when the molecule is not perfectly symmetric, that's perhaps an imprecise terminology, but we'll use it for now to sort of contrast what we just saw. So if you don't have perfect cancellation of those dipoles, if the molecule is not doesn't have the right symmetry to do that, the bond dipoles don't cancel out and a net dipole results. So the classic example of this is our good friend water, which is a really silly simple one. So we saw on the last slide, if you have a linear triatomic molecule, the two dipoles cancel each other out. But if we have a bent triatomic like water, remember that water is AX2E2, so it's going to be bent. There's two lone pairs on oxygen that are sort of into and out of the plane as I've drawn it in the other directions, but we don't really care about the lone pairs for this. So if we think about the polarity of the bonds in water, oxygen is more electronegative than hydrogen, so there's going to be a dipole that points from hydrogen to oxygen, and there's going to be one also pointing from the other hydrogen to oxygen. So you have two bond dipoles both sort of pointing at each other, but they don't cancel out in this case because they're not 180 degrees apart. They actually reinforce in the vertical direction as I've drawn it. And so what you get in net is you have reinforcing dipoles in this case. They don't cancel, and in fact they reinforce because they're sort of pointing in the same direction. And so the net molecular dipole for water, as I've drawn it in this orientation, is going to be vertical. So you'll have a net dipole moment that points, again, towards the more electronegative atom, but it represents a distribution, an unequal distribution of charge over the entire molecule. All right, so the two vectors come together, and the product, or the sum of those two vectors is going to be pointing straight up, and you're going to have net polarity pointing towards oxygen. All right, so those are two sort of examples of the extremes, and then finally, a more subtle situation arises where it sometimes is possible to have the same shape. So it's not just determined by the shape, unfortunately. There's a little bit of subtlety here where, as we saw in the last two examples, the first set of molecules we drew that were nonpolar didn't have any lone pairs. So we might want to maybe conclude that, if it doesn't have lone pairs, it's nonpolar, and that's usually true. But it is possible to have polar molecules without lone pairs as well. So molecules without lone pairs can be polar, and we're talking about lone pairs on the central atom specifically, not in total. But that's only if they have more than one type of outer atom. Okay, so let's do, we saw that CO2 was nonpolar because the two dipoles canceled. But let's say instead we had COS. So it's isostructural, but now you have an oxygen on one side and the sulfur on the other side. So the carbon-oxygen is going to be a very polar bond. Carbon and sulfur, I think they're very similar electronegativity. Sulfur might be a little bit more electronegative than carbon, but they're very close. So you'd have, if anything, just a really small dipole pointing towards sulfur, but not much of one at all. So you have one polar bond, one bond that's largely nonpolar or very weakly polar. And so in this case, you're going to have a net dipole. It's going to be polar, and you're going to have dipole pointing from right to left because the dipole that's associated with carbon and sulfur is smaller than the dipole that's associated with carbon and oxygen, so they don't cancel each other out in this case. Or in other words, if you imagine the two atoms playing tug of war for electrons, the oxygen is pulling stronger than the sulfur is, so there's going to be a net pull towards oxygen, even though the sulfur does partially cancel it out, but not completely. So if you have a situation where you have two different outer atoms, you have to think about the relative electronegativities of those and decide if it's going to be polar or not. Or another example would be if we had, so we saw that CF4, carbon tetrafluoride, was nonpolar. All of those canceled out. But if we had CHF4 instead, so it's still tetrahedral, but in this case we have dipoles pointing towards fluorine just like we did before, But then on the other side we have a CH bond, and carbon is a little bit more electronegative than hydrogen. Again, not by a lot, but it's slightly polar, but it points in that direction. So in this case you have 3 dipoles pointing in one direction that aren't canceled out by the other. They're actually reinforced in some sense, so this would also have a net downward pointing dipole towards the more electronegative molecules, or atoms, sorry. All right, so these are situations where even though they don't have any lone pairs on the central atom, if you have 2 different atoms bonded to that, the dipoles don't cancel each other out. All right, so those are some details and some situations that arise for different geometries. In reality, what you're going to be asked to do on homework assignments and exams is just predicting the molecular polarity. Okay? So, we're going to, like I said, we're going to ask you, is this polar or nonpolar, or which of these is polar or nonpolar, and so on. So there's some very simple things you can do to make some predictions. So if we have AXN molecules, should it be M? AXN, sorry, this should be M is in our notation. So we're doing the AXE notation, where M and N are the subscripts of telling you how many of each you have. But if you have no lone pairs, so if we have an AXM structure where all of the X's are the same, so CO2 would be an example, BF3, CF4, the ones I gave you on that first slide earlier. So if you have all X's the same and there are no lone pairs on the central atom, all of these would be nonpolar. Right? It doesn't matter how many atoms you have bonded to the central atom. If they're all the same and there are also no lone pairs in the central atom, those will be nonpolar. Yes? Yeah, no lone pairs on the central atom. There are no lone pairs on the central atom. Thank you. So in those situations where basically n equals 0 in this notation, that would be a case where they're nonpolar. All right, so if you know that that's the situation you have, you don't have to even necessarily draw the whole thing out or think about the dipoles and whether they cancel each other or not. This situation will always give you nonpolar molecules. All right, so let's do one example of the type of question we'll ask you. So we're going to give a series of formulas, SO2, SF6, PCl3, PCl5, and we want to determine which are nonpolar. All right, so all of these fit the criterion of having a central atom and only one type of atom bonded to the central atom. So we can know then if they don't have any lone pairs in the central atom, they're going to be nonpolar, but we have to figure that out. So for SO2, I'm not going to go through all the gory details, but SO2 has a total of 18 valence electrons because there's 3 group 6 elements, so 3 times 6 is 18. And if we draw the Lewis structure for this, we would start with this structure here. 2 octets is 16, so that does leave a lone pair for the central atom. If we want to complete the octet on the central atom and minimize formal charge, we would want to draw a couple double bonds and make this structure here. So I'm skipping through a lot of those details. Now, as I said before, for VSEPR, and by extension for molecular polarity, you don't have to have a perfect Lewis structure. We could have stopped here. As long as we know how many atoms are bonded to the central atom, as long as we know how many lone pairs it has, that will give us the geometry and that will then give us the polarity. So, we don't have to go all the way here. But this is the best Lewis structure that we would get if we want to minimize formal charges. So this is AX2E, and if you remember last time, that gives us a bent geometry. So really the correct way to draw this in 3 dimensions would be with a bent bond angle like that. And so in this case, it's going to end up being polar. Okay, so for triatomic molecules, molecules that have 3 atoms only, we talked about last time there's only 2 possibilities, linear and bent. Linear molecules will be nonpolar if the 2 outer atoms are the same. Bent molecules will be polar regardless of whether the 2 outer atoms are the same. Okay, so that's a pretty simple situation for this one. It's bent, so it's going to be polar. And then if we do the rest of them quickly, SF6. When we draw the Lewis structure for this, we end up getting an AX6 geometry. So there are no lone pairs on the central atom. This is octahedral. And even without drawing it, we know that because it's AX6 and has no lone pairs on the central atom, it will be nonpolar. And so all of these sulfur-fluorine dipoles will be canceled out by one that's opposite to it 180 degrees apart. So this is nonpolar. But just by virtue of knowing that it's AX6 with no lone pairs, we could have said that already. And then for PCl3, we did this one in class, I think a couple times. We got that it was AX3E. So PCl3 is our other one, AX3E. Well, this one's going to have a net dipole because we don't have full cancellation of all of those. I'll give you a table here in a second that's going to summarize all of this. And then finally for PCl5, which is the last one in the series, so this one's polar. And then finally PCl5, we get, this is an AX5 structure, so it's going to be trigonal bipyramidal, no lone pairs on the central atom, so it's going to be nonpolar. Okay, so in this case here, SO2 is polar, PCl3 is polar, SF6 and PCl5 are nonpolar, which is what we're looking for, so that makes the correct answer B. Okay, so we have to be able to distinguish polar from nonpolar molecules, and that comes directly from the VSEPR AXE notation and the geometry that results for that. So what's going to help you then when you do these is this table, which is an extension of what I showed you at the beginning. So this is a summary of VSEPR, and then it also tells you which of these are give you nonpolar and polar molecules. The key point, though, is that for this to work, all X's must be the same. If you have two different outer atoms, you need to then consider the arrangement of those and whether the bond dipoles cancel out. But if you have all X's the same, as we said, all of the AXM structures with no lone pairs, this whole column here, all give you nonpolar geometries. If you have one lone pair, it will be polar, so you don't have to even think about it. There are no examples of nonpolar molecules with a single lone pair on the central atom, so all of these are polar. If you have two lone pairs, then you have two that are polar, one that is not. And this one is square planar, so in that case the dipoles cancel out. And then the last one, which is another linear example, is also going to be nonpolar. So you don't have to necessarily memorize this, but it helps you to think about the different possibilities in recognizing some shortcuts you can take, which is that if it has no lone pairs, it will be nonpolar. If it has one lone pair, it will be polar. And then the ones that have more than one lone pair are a little bit of a mixed bag. But that's only true if all of the X's are the same, that this is going to necessarily be true. Okay? So any questions on this topic before we move on to the next part? Okay, so this was, as I said, a little bit of an extension of what we did last time and our ability now to predict molecular polarity using the shape. What we're going to talk about for the rest of today is we're going to begin to talk about bonding in covalent molecules. Okay? So we're going to talk about two different bonding theories in this course, a relatively simple one and then a more complicated one. So if we're going to form covalent bonds, as we said, the two atoms that are forming the covalent bonds, they share a pair of electrons. And so how does that look then from an orbital standpoint? So each atom has its own atomic orbitals where those valence electrons are going to reside. And then when they come together to overlap and form a covalent bond, what happens with the orbitals that those electrons were part of? So the simple bonding molecule we're going to start with is called valence bond theory. And at the simplest level, so what valence bond theory basically says is that each atom has its own atomic orbitals associated with it, and then those orbitals overlap to form the bond. So when you have a covalent bond formed, you have two overlapping orbitals, and the two electrons that are shared sort of stay in the overlap region of that orbital. But it's still two separate orbitals that are overlapping with each other. That's the key distinction of valence bond theory. So for very simple molecules, we can just consider the atomic orbitals and how they overlap. So if we want to make H2, we want to combine two hydrogen atoms. So remember, in hydrogen, we have a single electron that resides in a 1s orbital. We're going to combine that with another hydrogen, which also has a 1s electron. And so if we want to form a bond between these two hydrogen atoms, what the valence bond theory supposes is that the two 1s orbitals from each hydrogen overlap with each other. And so what you get then is two overlapping 1s orbitals with sort of an overlap region in between, like they should be the same size. So you have two overlapping 1s orbitals to make H2. And the two electrons that are shared spend most or all of their time. This doesn't really have a quantum theory associated with it, but they would be in the region that is overlap between those two orbitals. So this is what valence bond theory says for, for simple diatomic molecules. You can just assume that the atomic orbitals themselves are overlapping. And similarly for Cl2, it's a little bit different situation. So for chlorine, the valence electron configuration is 3s2, 3p5. So the place where we have an unpaired electron in chlorine is in the 3p orbitals. So for forming a bond between two chlorines, we would then assume we have filled 3s orbitals, so those can't overlap. Oh, stop writing. Now it's back. So the 3s orbitals are filled in chlorine, so if we're going to overlap two orbitals to form a bond and share electrons, we're going to use unpaired 3p electrons. A key point in all of this is that when we're forming covalent bonds, it's only the valence electrons, the valence orbitals that are involved. So that's never going to be not the case. But here for chlorine, we have our unpaired electrons are in 3p orbitals. So if we want to form a bond between two chlorines, we have an unpaired 3p electron on one chlorine. We're going to have another chlorine that's identical with its unpaired 3p electron. And then those two can overlap to form a bond between the chlorines where the two 3p orbitals overlap each other. And the electrons are right there in the middle. I didn't draw that particularly large, but that's where the electrons are shared. The like phases overlap each other. And you have two overlap 3p orbitals to form your Cl2 molecule. Okay, so this is again the simple case where it's just a simple diatomic. You overlap the atomic orbitals, and the electrons that form the bond are in that overlapped region of these two orbitals. And then we can do it for heterodiatomic molecules that have two different atomic orbitals involved. So if we have our 1s electron from hydrogen and our 3p electron from chlorine, we can overlap those to make a hydrogen-chlorine bond. So we're going to take our hydrogen 1s and then our chlorine 3p, and we can overlap those to make a bond where it's still the 1s orbital on hydrogen overlapping with the 3p orbital on chlorine, and the two electrons that are shared are in between where they overlap. Alright, so this valence bond theory still supposes that the individual atomic orbitals are preserved. So an atomic orbital from hydrogen overlapped with an atomic orbital for chlorine, or two atomic orbitals from chlorine overlap with each other, and not that you're creating new orbitals. Now there's a complication that arises, though, for the valence bond approach if we want to start thinking about more complicated molecules. Okay, so if we have a linear geometry, we need to form two identical bonds here. So the example I'm giving here is beryllium chloride, which is linear. So in this case, if we think about it, the valence electrons for beryllium has two valence electrons. They're both in a 2s orbital. So if we look at the central atom beryllium over here, its valence electron configuration is given as such. Energy increases as we go up. So the configuration for beryllium is 2s2, is this valence configuration. So the question becomes, how does this, if it has two paired electrons in a 2s orbital, how is it going to overlap with two other orbitals on chlorine to make bonds? Because you already have two electrons in that orbital that are paired. We can't violate the Pauli exclusion principle and shove more into there. So, what happens here? What happens is what's called hybridization. So for molecules that are not just simple diatomics, we have to mix atomic orbitals to make new hybrid orbitals. And so what happens here is that one of the 2s orbitals on beryllium is going to mix with one of its empty 2p's. So we're going to do what's called hybridization, where we mix an s orbital and a p orbital and get two new hybrid orbitals that are sort of a combination of those. So we would call these sp hybrids. They're going to be at an intermediate energy level between the s and the p orbitals. You can almost think about it as mixing the mathematical functions together. So each of these orbitals is represented by a mathematical wave function, and we're just adding those wave functions together to get new wave functions that we represent as sp. Now, all of this stuff that I'm showing you here is going to give you kind of the origin and the theory behind hybridization. Most of what you'll do in this course is just being able to predict what is the hybridization of the central atom. So we'll get to that more later on, but let's just talk about some of the details first. So when you have a linear molecule, you hybridize the s and p orbitals, and so now the two valence electrons on beryllium are going to end up in two degenerate orbitals like this. And then these are going to be our unhybridized 2p orbitals. So the energy of these is going to be between that of s and p, and they're going to be singly occupied now. And the energy of these is going to be unchanged, those are unhybridized. And so then what it looks like in this beryllium chloride molecule is that your beryllium has two sp hybrid orbitals that are going to be oriented in a linear fashion, each with one electron, and it's those that are going to overlap with the atomic orbitals from the chlorine. So your beryllium is going to look like this, and then your chlorine is going to come in with its 3p electrons. And it's going to overlap with those. So really the electrons would be in the overlap region between those, just like we saw before. And that's how you're going to form the bonds. And this beryllium would still have two unhybridized 2p orbitals that are empty in this case. So the two valence electrons from beryllium end up in hybridized sp orbitals that are at the same energy and that are 180 degrees apart. And then those overlap with the chlorines to form this linear BeCl2 molecule. Okay? So that's the picture of hybridization. We're mixing atomic orbitals on the central atom to make new orbitals that are in the correct geometry to form whatever molecule we're forming. So that one was the start. Now let's talk about if we have a trigonal planar electron group arrangement. And this is, I think, where the picture for hybridization becomes even more clear why we even need it. So if you think about BF3, that's a classic example of a trigonal planar molecule. So again, the valence configuration for boron by itself is going to be 2s2, 2p1. And so how would you form three bonds with this arrangement? You already have two paired electrons up here. You only have one unpaired electron, and it's in a 2p orbital. Even if we were to somehow promote these 2s electrons into 2p, if you think about the three 2p orbitals, they're all 90 degrees from each other. Right? We have px, py, and pz. So even if you had one electron in each p orbital, they'd be 90 degrees oriented. How would you make a trigonal planar molecule with 120 degree bond angles? You can't do that with just using atomic orbitals. So in order to form a trigonal planar molecule with those 120 degree bond angles, you need to mix the central atom atomic orbitals to make hybrid orbitals. So in this case, if we're going to form three bonds, we need to hybridize three orbitals. So we're going to hybridize our 2s orbital, and we're going to hybridize it with two different 2p orbitals. So we use two 2p orbitals, and that gives us a set of what we call sp2 hybrid orbitals. So because we've mixed one s and 2p, we call it sp2. You get three identical hybrid orbitals, and when we put the three valence electrons from boron in there, they're now going to arrange themselves like this to follow Hund's rule, and that gives you then three identical singly occupied orbitals that are available to form three bonds. Okay, so these three are going to overlap with the outer atoms, in this case fluorine if we're using this example, and they're going to form the three identical bonds, and they're going to be arranged 120 degrees apart. All right? So that's how it works for trigonal planar. And then the last one we'll talk about in detail is if we have four electron groups instead of three. So in this case, we're going to be talking about the tetrahedral geometry, which is AX4. So a classic example of that is methane, CH4. So the electron configuration for the central atom carbon is 2s2, 2p2. All right, so again, if we consider the unhybridized regular old atomic orbitals, there's only 2 unpaired electrons available to try to form 4 bonds, so we're forming CH4. And those 2 orbitals are oriented 90 degrees apart. The tetrahedral bond angle is 109.5. So clearly, simple atomic orbitals aren't going to work again. And if we want to form 4 bonds, we have to hybridize 4 orbitals. So we're going to take that 2s orbital and we're going to mix it with all 3 of the 2p orbitals to form a set of identical sp3 hybrids. All right, so you'll notice there's always a conservation of orbitals. We're starting with 4 atomic orbitals, so we're going to make some combination of 4 hybrid orbitals or unhybridized atomic orbitals. So if you start with 4 orbitals, you end up with 4 orbitals. In this case, we're mixing all 4 of them, so we get 4 identical orbitals that we call sp3, and the 4 valence electrons from carbon go into those equally. They distribute equally to follow Hund's rule, and then you're going to be able to pair these with the atomic orbitals of hydrogen to make your 4 CH bonds that are going to be 109.5 degrees apart. They're all at equal energy. They're all arranged 109.5 degrees apart, and that explains the ability to form 4 identical CH bonds. Okay, so that's what we have for sp3. Now, another example of sp3 that I want to go to is you might be wondering, what happens if we have lone pairs? Yeah? So we're mixing 2s and all 3 of the 2p orbitals. So it's a total of 4 orbitals that we're mixing together, and that gives us a total of 4 hybrid orbitals. In the previous examples, we didn't mix all of them. We mixed, in this case, the 2s with 2 of the 2p's. That would give us 3 hybrid orbitals, sp2, and then we'd have one, I forgot to label it, one unhybridized 2p. Okay, so whenever you have sp or sp2 where you're not using all the orbitals, you're still going to have some unhybridized orbitals that are available. And we'll talk about the importance of those here in a little bit. But in this case, for sp3, when you're using 4 orbitals, you form 4 hybrids, and you don't have any unhybridized orbitals left over. Well, let's see what happens if we have lone pairs. So if we have NH3, this is going to be the Lewis structure of NH3. Why is part of this missing? There it is. No, it has a mind of its own today. All right, it's back. Just had to get away from it for a second. All right, so then NH3 is AX3E. So this has still 4 electron groups, but then how do we explain the lone pair and the hybridization, and where does that lone pair go? So the point that I want to make here is that hybridization correlates with, and we'll see a table in a little bit that summarizes this, but hybridization correlates with electron group arrangement. All right, so we just got done saying that methane CH4, which is AX4, no lone pairs, is going to be sp3 hybridized. That has a total of 4 electron groups. NH3 also has 4 electron groups. It also has a tetrahedral electron group arrangement, so it will also be sp3. And so the way this works for ammonia is that if we look at the central atom nitrogen, nitrogen is 2s2, 2p3. All right, so again, you might be tempted to just, this only has 4 bonds. Let's just use the unhybridized 2p orbitals. But don't forget that these 2p orbitals are 90 degrees apart. The bond angles in NH3 are so close to 109.5, so we have to hybridize the orbitals to put them in the correct angle to form the tetrahedral electron group arrangement. So we still hybridize our s and our p orbitals. That gives us, again, an identical set of 4 sp3 hybrid orbitals. We mixed all of them in this case. And then if we put the 5 electrons in there, there's 5 electrons, valence electrons on nitrogen. And so if we fill them, what we get is this arrangement. The 5th one has to go back in and pair with that first one. And this one here that has a pair of electrons, that's our lone pair. Our non-bonding electrons, as we call them. And then these 3 here are going to form our 3 NH bonds. Okay, so all of the electron groups are still 109.5 degrees apart, but now one of those electron groups is a lone pair that doesn't overlap with hydrogen atomic orbitals, and 3 of those still do. Alright, so that's kind of the theoretical backdrop for hybridization. It shows us that we have atomic orbitals that mix together to form these hybrid orbitals, and then that results in orbitals being in the correct disposition to form the different geometries that we talked about. But in reality, what you're going to have to do on the homework assignments and the test is just predict the hybridization. So we're going to give you the formula for a molecule, and we're going to say, what is the hybridization of the central atom in this molecule? And you're going to have to then draw the Lewis structure and correlate that to hybridization. So the way that this works is all that matters for this is what's called the steric number. Remember, steric number is the total number of electron groups. Or if you're a devoted follower of the AXE notation, this is that n plus n, the total number of electron groups that you have, total number of atoms plus the total number of lone pairs. And the hybridization is determined entirely by that. Okay, it doesn't matter what combination of m and n you have. If you just look at the central atom and identify how many electron groups are bonded to it, you can immediately determine the hybridization. And so the way you do that is you just count the number of, you look at the steric number, and that's going to be the number of orbitals that end up hybridizing. So you have a steric number of 2, like CO2, you need to hybridize 2 orbitals, so we pick the first 2. So the atomic orbitals that are available for hybridization are an s orbital, 3 p orbitals, and then sometimes we have to invoke d orbitals, as we'll see as well. But if you need to hybridize 2 orbitals, you pick the first 2, s and p. That gives you sp hybridization. And that correlates then with the linear electron group arrangement that we would expect for an AX2 molecule, or any other combination of 2 electron groups. If we have a steric number of 3, so now we're talking about the trigonal-pyramidal electron group arrangement. I should probably change this from geometry to electron group arrangement. That's a little bit more precise in this case. Okay, so if we have steric number of 3, we need to have 3 orbitals hybridized. So we take the first 3 that are available, sp, s, and 2p's, and that gives us sp2. All right? So this is going to give us a trigonal planar electron group arrangement. So any molecule that has a trigonal planar electron group arrangement will be sp2 hybridized at the central atom. All right? 4 electron groups, we take the first 4 of these orbitals, and that gives us sp3. So s and 3p's is sp3, and this correlates with the tetrahedral. Now the other 2 electron group arrangements, we haven't talked about them yet today. You can have steric numbers of 5 or 6, 5 being trigonal bipyramidal, as we talked about. And 6 being octahedral. So those 2 higher order electron group arrangements also can, by the valence bond approach, by the valence bond theory, would also have hybridizations associated with them. Now in this case, because you have more than 4 electron groups, we have to go beyond 4 orbitals and start using the d orbitals, because there's only 1 s orbital and 3 p orbitals available for hybridization. So if we're going to hybridize 5 orbitals, we need to include then a d orbital. Right? So we have sp3d. Now in this part of the course is when I really feel bad about myself, because I really am kind of lying to you guys. More advanced bonding theories that are available today show that the d orbitals don't really participate in bonding for main group molecules. If we're talking about transition metals, they do, but for main group molecules like we're dealing with for VSEPR, you don't really have participation in the d orbitals. But this type of hybridization that invokes d orbitals in the context of valence bond theory was commonly used to rationalize these geometries, and it is still often referred to today, and you will see it in this course on the homework assignments and tests. So I just want to point that out, that you don't really, in reality, the d orbitals don't participate, but if you have 5 electron groups, the way the hybridization is going to be indicated for that is sp3d. So you need a total of 5 orbitals to hybridize. So you're going to take your s orbital, you're going to take all 3 of your p orbitals, and then you need 1 more, so you include a d orbital to make it sp3d. Or sometimes dsp3, the order doesn't really matter, but those are 2 different notations for 5 electron groups, gives that hybridization. And then finally, for 6 electron groups, we need to take the first 6 in this list. So you'll never use more than 2 of the d orbitals. In this case, we use 2 d orbitals along with sp and s and 3 p's, and that gives us sp3d2. All right, so again, it's a little bit of a fib that the d orbitals are actually participating, but to rationalize these higher order geometries, we include those in the hybridization to give us sp3d or sp3d2. So really, to determine the hybridization, you just need to be able to count the number of electron groups, and from there, it comes straight out of that. You don't have to worry about any of the other details about that structure. Okay. So some examples of hybridization. Let's do hybridization of the central atom in COCl2. All right. So I don't want to spend a lot of time on this because we have a lot to get through today. But if we draw the Lewis structure for COCl2, we end up with a carbon-oxygen double bond. We have lone pairs all over there and 2 there. So that's the full Lewis structure for COCl2. We need a carbon-oxygen double bond to complete the octet on carbon, and it also removes formal charges as well. And so this is the structure. And if we want to know the hybridization of the central atom, we just need to figure out how many electron groups are bonded to our central atom. So if we use the AXE notation, this is an AX3 structure. The steric number, or the number of electron groups in total, is just 3. Because there's 3 things attached to our central atom, 3 atoms, no lone pairs. Remember, when you're counting steric number or number of electron groups, it doesn't matter whether it's a single or double bond, it just counts as 1 electron group. So this option is 1 electron group, 2, 3 for the chlorines. Steric number is 3, we need to hybridize 3 orbitals. We have an s and 3 p's available. We need 3 of those to be hybridized. That gives us sp2 hybridization. All right, so just like we saw for VSEPR, if you're going to predict hybridization, you need a good Lewis structure. So Lewis structures, which is one of the topics we covered in Chapter 3, and which will be on the exam this week if you haven't taken it yet, Lewis structures are still very important in Chapter 4 for doing the molecular shape as well as the hybridization like we're doing here. But that's all you need is a good Lewis structure, and then from the number of electron groups, you can get hybridization. Now, sometimes we'll also ask you a little bit more complicated ones. So we'll give you these bigger Lewis structures, and we'll ask you to determine the hybridization of 1 or more of the atoms in this molecule. And so the first thing we have to do in this one is we have to complete the Lewis structure. Now, there could possibly be exam questions like this. This will be helpful for those of you that haven't taken the exam yet. So we have this, what's called a carbohydrate, which is carbon, hydrogen, and oxygen. When you have these longer, bigger molecules like this that mostly have carbon, oxygen, nitrogen, hydrogen, these are what are called organic molecules. And all of the non-hydrogen atoms are going to want to complete their octet, and they're going to want to have 0 formal charge in almost every case. And so when you have carbon in structures like this, to complete its octet, it's going to make 4 bonds, and it's going to have 0 lone pairs. All right. For hydrogen, as we said, it's always going to just form 1 bond, so that's still the same. When you have oxygen in structures like this, they tend to form 2 bonds and have 2 lone pairs. And then finally, for nitrogen, 3 and 1. And then if you have a halogen in one of these as an outer atom, so fluorine, chlorine, bromine, iodine, not as a central atom, but as one of the outer atoms, those will have 1 bond and 3 lone pairs. All right, so all of these non-hydrogen atoms want to get their octet, their 8 electrons, and they're going to do that in different ways. Carbon is going to have 4 bonds for a total of 8 electrons, but no lone pairs, and so on. Different combinations for the other ones to minimize formal charge. So if we want to complete the Lewis structure of this to figure out the hybridization, what we need to do is look at all the carbon atoms in the structure and figure out if they have their correct number of bonds. So this first one already has 4 bonds. 1, 2, 3, 4. But this second and third carbon here, you notice they each only have 3 bonds. So the way we can fix that is by drawing a double bond between them. Now they both have 4, so they're happy. This carbon already has 4 bonds, 2 to carbon, 2 to hydrogen. This one here only has 3 bonds, and then this oxygen only has 1. So carbon wants to have 4 bonds, oxygen wants to have 2 bonds. We can fix that by making another double bond there. And then finally, these last 2 carbons here, each of them only have 2 bonds. We cannot draw any more bonds from this carbon to the one before it, because the one before it already has its 4 bonds. So if we draw 2 more bonds here as a triple bond, that will now result in both of these carbons having exactly 4 bonds and still no lone pairs, as you'd expect for carbon. So to complete the Lewis structure, we had to add in a few multiple bonds. It turns out for this problem, it's not even that important to do that, because for hybridization, we just need to count the number of electron groups, and we don't really care if they're singly, doubly, or triply bonded. So in this case, that was not necessary, but it's still good to go through it anyway. So if we look at this carbon here, this carbon has 1, 2, 3, 4 things attached to it, so it's going to be sp3. It's going to hybridize 4 orbitals. These 2 carbons here, both of them have 3 electron groups. They're bonded to 2 carbons and a hydrogen each. So for 3 electron groups, you're going to get sp2. This carbon here is still attached to 4 electron groups, 2 carbon-carbon bonds, 2 carbon-hydrogen bonds, all single bonds, so that's sp3. This carbon, 3 electron groups, 2 carbon-carbon bonds, 1 carbon-oxygen bond, total of 3 things bonded to it, so it's going to be sp2. And then these last 2 here each have 2 electron groups. It's bonded to a carbon on one side, a carbon on the other side. That's going to be sp then, because there's only 2 electron groups. This carbon also has 2 electron groups, a carbon to the left of it, a hydrogen to the right, giving us sp hybridization when you have 2 electron groups. So if you can finish out the structure, count the number of electron groups, the hybridization comes right from there. Okay? All right, questions on this topic? Okay, so the last thing we want to cover today in the context of what's called valence bond theory, which is this localized bonding theory that assumes that individual orbitals on each atom overlap with each other, are the different types of bonds that we have. All right? So it turns out that every bond involves overlapping electrons, but there are 2 different ways to do this. Technically 3 different ways if you include transition metals, but we're not going to include those here. But for the types of molecules we're talking about, we have 2 different types of bonds, and they're abbreviated by Greek letters, sigma and pi. All right, so let's first talk about sigma bonds. So sigma bonds are formed by end-to-end overlap of atomic or hybrid orbitals. So a key point I want to make, which I'll make now and then emphasize periodically throughout, is if you have hybrid orbitals on your central atom, those hybrid orbitals will only form sigma bonds. It's the only kind of bond that hybrid orbitals can form, are sigma. But sigma bonds can also form from unhybridized atomic orbitals as well. And so what's the definition of it? So it's going to be, in a sigma bond, you're going to have the electron density, which is going to be the overlapping electrons for the 2 atoms. It's going to be greatest in between the nuclei. So each atom has a nucleus. And the electron density for sigma bond is greatest in between the nuclei along the bond axis. All right. And so, as we already said above, the orbitals that are involved are atomic and or hybrid orbitals. And to put it in writing again, hybrid orbitals will only form sigma bonds. All right, and so the pictures that I drew at the beginning of this section, where we were talking about the overlap of atomic orbitals, that's basically what a sigma bond looks like. You have 2 orbitals, they approach each other head to head, and the 2 orbitals overlap right in between the 2 nuclei. So if we took 2 s orbitals, you have your nucleus in the center here, and so if we overlap those, we could form a sigma bond where you have overlap in between the nuclei. And so for this sigma bond, your overlap region is in between the 2 nuclei, right along the line segment that connects them. Or if we overlap 2 p orbitals together, You would form a sigma bond by overlapping them head to head with each other. Where your two nuclei are there at the center of each p orbital, and the overlap region is once again in between the two nuclei right along the bond axis. So that's what we call a sigma bond. It's head-to-head overlap of the two atomic orbitals or hybrid orbitals, whatever the case may be. All right. Now the other type of bond that we're going to have are going to be called pi bonds. So adding to our Greek alphabet soup, we have also pi bonds now. I'm sure most of you are already familiar with the Greek letter pi, given its widespread use in geometry. So pi bonds are a little bit different. This is going to be side-to-side overlap of orbitals. So instead of head-to-head, it's side-to-side. And so what it results in is regions of electron density above and below the internuclear axis. Where the bond axis being the straight line that connects the two nuclei that are, I guess, the straight line segment that connects the two nuclei that are bonding to each other. Now, the orbitals that are involved in forming pi bonds are always going to be unhybridized p orbitals. Okay? So we saw that some electron group arrangements, particularly the linear AX2, which gives us sp hybridization, or if you have 3 electron groups, sp2 hybridization, those hybridizations always leave 1 or 2 unhybridized p orbitals, and if you're going to have pi bonds, it's going to be those unhybridized orbitals that are going to form pi bonds. You will never have s orbitals that form pi bonds, and you'll never have hybrid orbitals forming pi bonds, only unhybridized p orbitals. So the way this looks is, as I said, it's a side-to-side overlap, so we take 2 p orbitals that are arranged side to side with respect to each other, and they're going to form what's called a pi bond, which is overlap above and below the bond axis. So let me actually draw a little bit differently. So you have your 2 nuclei, the bond axis is right between the 2, but then the overlap is going to be above and below that axis, this sort of side to side arrangement of the 2 orbitals, where you have shared electron density in these 2 p orbitals that come close enough together to overlap with each other like that. Okay, so it's above and below the bond axis. It's unhybridized p orbitals that do this, and it's distinct from sigma bonds because the the shared electron density is above and below the axis, not between the axis, between the nuclei. Okay, so those are the 2 types of bonds. That's what they look like pictorially, and those are the types of orbitals that can be involved in forming those bonds. The bigger question that you're going to be addressing in homework questions and test questions is how many of each bond type are there? So if we look at the structure of a molecule and we consider the single and the double and the triple bonds that are there, how do we know which ones are sigma? How do we know which ones are pi? And so what valence bond theory tells us is that if we have a single bond, remember a single bond is a bond that just involves sharing 2 electrons between the 2 atoms, all single bonds are going to be sigma bonds. Now again, I should emphasize that this is only true using what's called valence bond theory that we're talking about today. We'll talk about another bonding theory next time that's a little bit more complex mathematically. In that one, it is possible to have a single bond that's a pi bond. But in this case, if you have a single bond and you're using hybridization or hybrid orbitals to invoke the formation of that single bond, it's always going to be a sigma bond. If we have multiple bonds, so a double or triple bond, those always consist of 1 sigma bond as well. But then the rest of the bonds that are involved in that multiple bond are going to be pi. So for main group molecules, the only multiple bonds we have are double and triple. So if you have a double bond, which is when we draw a Lewis structure, that would be 2 lines in between the atoms sharing 4 electrons. That's going to be 1 sigma bond, and then the other bond, the second bond, is going to be pi. And then if you have a triple bond, you always have just one sigma bond, and then the rest are going to be pi, so you have 2 pi bonds to make a total of 3 bonds. All right, so if you look at your structure, whether it's a simple Lewis structure with a central atom and a bunch of outer atoms, or if it's a more complicated one like we looked at earlier with a bunch of atoms in it and a bunch of different bonds, you just have to look at each bond and assign it. If it's a single bond, it's sigma. If it's a double bond, it's sigma plus pi. If it's a triple bond, it's sigma and 2 pi's. Okay? All right, so then I guess we're going to get done a little bit early today because this is the last thing I have is this one here. So if I give you this more complicated structure here, and I'm sure in the week of an exam nobody will protest leaving early. But anyway, we want to know, if we have this structure here, we want to know how many sigma and pi bonds are in the molecule below. As I said, each single bond is sigma, and then each multiple bond is sigma, and the rest are pi. So if we look for the single bonds first, all of those we can label as sigma. So this carbon has 4 single bonds, they're all sigma. All of our bonds to hydrogen will be sigma because they have to be hydrogen. They have to be single. Sorry, they have to be single. Those are all sigma, sigma, sigma. So all of the single bonds, the bonds that are represented as a single line, will be sigma. And then finally, if we look for the multiple bonds, we have a double bond here. That's going to be 1 sigma and 1 pi. We have another double bond here. That's going to be 1 sigma and 1 pi. And then finally, this triple bond here is 1 sigma, and it's going to be 2 pi's. All right, so you have sigma and pi combinations whenever you have multiple bonds, but it's always just going to be 1 sigma bond, never more than 1 sigma bond for a single bond between 2 atoms. And so finally what we find is if we count this correctly, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 sigma bonds in this molecule. And then we have 1, 2, 3, 4 pi bonds. All right, and the last thing that I want to show, because I sort of skipped this detail, is when we form pi bonds, let's say we have, can I put a new page in? Probably not. All right, if we have, I should see if I can figure out how to do that. I don't know if I can put a new page in, but I'll try to fit it in here. So if we want to have pi bonding, if we have, let's say, CO2, which we know is carbon with 2 carbon-oxygen double bonds. So the sigma bonds are going to be formed by overlap of sp orbitals. This is sp hybridized. So on the carbon, we're going to have 2 sp hybrid orbitals, as we said, that are going to overlap with the oxygen orbitals. I guess this would be hybridized as well. So your sigma bonds are going to be formed by overlap of hybrid orbitals. So you get this sigma bond there, and then for the pi bonds, you're going to have unhybridized p orbitals. So you're going to have an unhybridized p orbital on the carbon. If it's sp hybridized, there's going to be 2 unhybridized p orbitals that are left over. Your oxygen is going to also have p orbitals. And so you're going to get this pi overlap above and below. So this double bond here between carbon and oxygen is 1 sigma bond that's formed by overlap of the hybrid orbitals in between the bond axis, and 1 pi bond that's formed by 2 unhybridized p orbitals. Now the other one's going to be harder to draw because the second p orbital has to be perpendicular to this. So you're going to have another p orbital that's sort of into and out of the plane, and they're going to form a pi bond that's at a 90-degree angle to that. Okay? So the second pi bond is also overlap of p orbitals, but it's rotated 90 degrees relative to the first one. All right, but each of these carbon-oxygen bonds is going to have sigma overlap between the hybrid orbitals and then pi overlap above and below to give you that combination of a sigma and a pi bond. All right, so that's what it looks like for a double bond. Each one is a sigma in between with hybrid orbitals and then unhybridized 2p. So we might ask you some questions on the homework about which orbitals overlap to form these different bonds. And so the sigma in this oxygen is also going to be sp2 hybridized because it has 3 electron groups. So the sigma bonds are going to be sp orbitals, sp on carbon and an sp2 on oxygen. So oxygen has 3 electron groups, so each of these is sp2. So the sigma bond is going to be an sp orbital on carbon overlapping with an sp2 on oxygen, and then the pi bond is going to be a 2p orbital on each atom overlapping with each other. Okay, so when we start talking about the types of bonds, we also want to think about the orbitals on each atom that overlap. And so the sigma bonds are overlap of hybrid orbitals. Carbon is sp hybridized, so it's going to use its sp hybrid orbital. Oxygen is sp2, so it will use that hybrid orbital. Those two overlap to form a sigma bond. And then unhybridized p orbitals will always be involved in forming pi bonds, regardless of the situation. All right, that takes us to the end. If we have any last questions, I'll address them now. And if not, I'll see you guys on Wednesday to try to finish out Chapter 4.